Welcome to this video on pH calculations. We're going to look in this video at weak acids. So we're going to think, first question we always ask is, what situation am I in? So weak acids here have got pKa's of bigger than 0 and Ka's of less than 1. So if we're in a situation where we look up the Ka and it's less than 1, we look at the pKa and it's bigger than 0, we're in a weak acid situation. And you can tell a pH calculation is for a weak acid in the context of exams, and because the Ka and, or, well, not really and, but or the pKa, Ka or pKa will be given. So you pretty much can tell from that you're dealing with a weak acid situation. So that's how you work out that you're dealing with a weak acid. What assumptions can you make? Well, in water, weak acids are going to be, if we look at this diagram, these grey molecules here are the weak acid molecules, and you can see there's a fair bit of association still of the HAs and relatively little dissociation into H3O plus and A minus. So in water, weak acids are partially dissociated. So we're going to look at how these different factors affect the pH of a weak acid solution. So here's my weak acid here. You can see partial dissociation. I'm going to stick the pH probe into this solution. I find at the moment it's reading a value of 3.94. And I'm just going to change a few different things about the solution and just have a look at what happens. So if I increase the concentration 10 times up to a value of 0.1, I can see here that I've got now more HA molecules. It's a little bit tricky to actually see from this what's happened to the dissociation, but if we look at the graph, we can see that if we increase the concentration here, the orange bar here representing the concentration of H plus is going to go up, and if we decrease the initial acid concentration, it goes down. So that's going to have an effect on the pH, and you notice if I increase the concentration, the pH number is going down as a result. So if I just reset that back to this value, let's look at the effect of the acid strength. So on the molecules, if we increase the strength of the acid, we should see more of those grey molecules becoming red and blue ones, and that's in fact exactly what we do see. So we're expecting the concentration of H plus is going to increase. So if we look here, if we increase the strength, we get more H plus ions. If we decrease the strength, we get a lower concentration of H plus ions. And look at the pH value. Stronger acid, the pH goes down. A weaker weak acid, the pH is going up. So what have we seen from the simulation? Well, the pH value is going to depend on the initial concentration of acids. So the more HA you have, that's going to affect it. And generally what we're expecting to see is this will, more HA is going to lead to a higher concentration of H plus and therefore a lower pH. So that's what we're expecting, and that's similar to a strong acid. But unlike strong acids, which are essentially fully dissociated, the acid strength or extent of dissociation, which is usually summarized by the Ka or perhaps the pKa, is going to again also impact the concentration of H plus ions and hence the pH. So again, the higher Ka we're expecting to see higher Ka leads to a higher H plus concentration and a lower pH, and that's what we've just seen on the simulation. So given that the Ka is going to be crucial, it would be useful to have a look at the Ka formula and see, can we forge a link between Ka and the H plus concentration? And it turns out we can. But in order to do it easily, we're going to make a couple of assumptions. So we're going to make some assumptions here. Assumption number 1. So assumption number 1 is a relatively obvious assumption, which is going to simplify this. At the moment we've got H plus which is the equilibrium concentration that we're interested in finding. We've got Ka that we know, but A minus is a bit of a pest. We don't really want that in the formula. But because if we look at the dissociation down here of HA, when one HA breaks up, it breaks up into one A minus and one H plus, or hydronium ion. And therefore we're going to make the assumption that the concentration of H plus ions should be the same as the concentration of A minus ions. And if you do some counting on this picture, you'll find that that's the case. It makes sense that it would be. Second assumption that we're going to make, assumption number 2, is we're going to say that actually that HA concentration, which we need in the equilibrium constant, which is at equilibrium, well, that's going to be quite difficult to work out because you're going to have to take the initial concentration and then subtract off any molecules that have dissociated. But if very few molecules have dissociated, then we can say that that equilibrium concentration is just the same as the initial acid concentration. So that's what this 0 here means. This is the initial acid concentration. We're saying here that very, very little has dissociated. And I have got a whole video where we examine these two assumptions, but for now we're just going to take them as being okay. So if that's the case, we can rewrite our Ka expression. It's now only approximate, and we can say, well, I've A minus, that's the same as H plus, so I've got two H pluses multiplied together on the top, so that's concentration H plus squared, and then on the bottom we've got the initial acid concentration over here. Now that's great because this is easy to know. You've controlled that as an experimenter. This value you can look up in a data book, and so we can rearrange this. Square of that, we're going to multiply both sides by the initial acid concentration, and then we can square root both sides and find this very important relationship. And this, for weak acids, is the key relationship that you need to be aware of. Now, before we have a go at some examples, it would be worth just seeing, does that actually make some sense? Well, over here we said if you've got more initial acid, you should have a higher H plus concentration. And that's exactly what we find here. It's H plus concentration. If you increase this value, you're going to get a higher H plus concentration. And similarly with Ka. If you've got a bigger value of Ka under here, you square root it, it's still going to be giving you a higher H plus concentration. So this formula makes sense. So with that formula in hand, let's have a go at trying to do an example calculation. So what is the pH of this concentration of hydrofluoric acid, which has got this Ka value? So, as always, pH is our goal, and H plus ion concentration is the crucial parameter that we need to then work out. So how are we going to get there? Well, we're going to make our two assumptions, that the H plus and A minus concentrations are identical, and that the equilibrium concentration of HA is just the same as its initial, with our approximate formula, and we're going to hope that that will give us a reasonable answer. So how does the solution proceed? Maybe pause and try and see if you can do it. So we can directly work out the H plus concentration here using our rearranged formula. And that's going to come out to be 6.76 times 10 to the minus 4 multiplied by the initial acid concentration, which is 0.5. And when you do that, that comes out to be 0.0183 moles per decimeter cubed. I really must emphasize the importance of the square root here. This is commonly missed. You've got to be really, really careful with that. So once we've got the H plus concentration, then we can just turn that into the pH using the normal Sorensen relationship. It turns out to give you a pH of 1.74. and that's how you work out the pH. So here's another example of a weak acid pH calculation where we're trying to find the pKa of a weak acid from a pH value. So here's the goal is the pKa that we're trying to find, and most likely that's going to come from the Ka, because we can easily convert pKa from Ka just by using the definition of the pKa. So we are going to work through the Ka as one of our stepping stones. If we look at the other information we've been given, we've got here this concentration of our acid. So this is our initial acid concentration. Now if you were to treat this as a strong acid, then this concentration should give you a pH of 1.04. So this is definitely in the realm of a weak acid. And we've actually been given also its pH value. So how are we going to do this? Well, we remember that our really important formula for Ka is that Ka for a weak acid is square of the concentration of the H plus over the initial acid concentration. And so as we know the initial acid concentration, if we can just work out the H plus ion concentration, we should be able to use that formula to derive what the Ka is and hence the pKa. And we can get the H plus concentration because we know that we've got the pH value, and if we can just reverse our definition of pH, we can find the H plus concentration in this way. So let's see how that actually works. So the H plus concentration is going to be 10 to the power minus 3.92. Again, there's no need for you to actually work that out. You can just simply use it in the calculation directly. The Ka is approximately equal to that value squared. Don't forget the squaring. Divide that by the initial acid concentration, which is 0.09, and we get from that an approximate value for the Ka of 1.61 times 10 to the minus 7 moles per decimeter cubed. And the pKa, if we do a negative logarithm of that, comes out to be 6.79 at least to 2 dP. So it's the same assumptions, but this time working in reverse from the pH to get to the Ka and hence the pKa.